Hey everyone, and welcome. Have you ever really stopped to think about the magic that happens when you hit send on an email, or when a movie just appears on your screen? I mean, it feels instant, right? But underneath all of that, your data is going on this absolutely incredible high-speed journey. So in this explainer, we're going to pull back the curtain and look at the real building blocks of the internet, from the tiniest signals in a wire to the massive, complex solutions that connect us all. Let's dive in.
So let's just kick things off with a question that sounds really simple but has this wonderfully complex answer. What actually happens in that split second after you click send? You know, your message doesn't just teleport. No, it gets completely transformed, it's packaged up, and then sent on this wild ride through a global network. And today, we're going to follow that little piece of data every single step of the way.
So here's what we've got on tap. First, we'll start with the absolute basics, the rules of communication. Then, we're going to figure out how our digital data gets turned into physical signals. After that, we'll see how in the world the network lets millions of us share the same info highway at once. We'll touch on securing those connections, and then the best part, we'll take everything we learned and use it to solve some real-world problems.
Okay, first things first. Just blasting a bunch of raw electricity or light down a cable, that's not enough. For that signal to actually mean something, there have to be shared rules and agreed upon structure. You know, it's the difference between just shouting random noise into a room and having a real, coherent conversation where everyone understands each other.
And this slide really nails a super important distinction. On the one hand, you have data communications. Think of this as the pure physics of it all, the engineering problem of just getting signal from point A to point B reliably. But on the other hand, you have networking. Now this is the logic, the architecture, the protocols. It's the set of rules, the shared language that lets a Samsung phone in Seoul have a perfectly clear conversation with an Apple server in California. One's about moving the signal, the other's about making sure that signal actually means something.
And this diagram, it's basically our map for the whole thing. It shows the entire process beautifully. You've got a source. That's you on your computer. It goes to a transmitter, maybe your router, which gets the data ready. Then it travels through the transmission system. That's the wild, complex thing we call the internet. And finally, on the other side, a receiver catches that signal and hands it off to the final destination. We're going to be breaking down what's really happening inside each of these boxes.
All right, let's tackle our first big puzzle. Your computer thinks in ones and zeros, right? That's digital data. But an Ethernet cable, it carries electrical pulses. And your Wi-Fi uses radio waves. So, how do we translate the language of the computer into the language of the wires, or the language of the air? Well, that is the art of encoding.
So it turns out there are basically 4 ways this translation can go down. First, the easy one, digital data to a digital signal. This is super direct. Your computer sends a high voltage pulse down an Ethernet cable for a 1 and low voltage for a 0. Simple. Second, we have analog to digital. This is how the real world gets into our computers. Think about your voice. It's a continuous analog sound wave. A microphone captures it and a chip converts it into a digital file, a stream of ones and zeros. Third, digital to analog. This is your Wi-Fi router's big job. It takes those digital ones and zeros from your computer and modulates them into a smooth, continuous analog radio wave that it can send through the air. And finally, you have analog to analog. Think of old-school AM radio. They take the analog music signal and just piggyback it onto a specific radio frequency to broadcast it out.
So what's the bottom line with all these methods? Why so many? Well, the goal is actually really simple. Encoding is all about being a perfect matchmaker. It's about pairing the format of our data with the physical strengths of the medium it's about to travel on. You wouldn't try to send a smoke signal through a fiber optic cable, right? It's all about choosing the right language for the right journey.
So, we've figured out how to send a single signal. That's great. But the internet isn't a private line from your house to Netflix. It's a massively shared resource. A single fiber optic cable running under the ocean has to carry the data from millions of people all at the same time. How do we share that one information highway without everything just crashing into a chaotic mess?
The answer is this absolutely brilliant idea called multiplexing. It's the art of taking a bunch of different streams of information, weaving them together into one single complex signal, shooting it over the line, and then, this is the magic part, perfectly unweaving them at the other end. It's the engineering that makes our shared networks even possible.
This diagram shows it perfectly. Look on the left. You've got all these different senders. Their separate data streams all funnel into this one device called a multiplexer, or a MUX. It cleverly combines them. Then that one combined signal travels down the shared line. Over on the right, a demultiplexer, or demux, does the exact opposite job.
It catches that big signal, carefully pulls it apart, and sends each original stream to its correct receiver. Pretty clever, right?
Honestly, the best way to think about this is with a traffic analogy. Just imagine dozens of little local roads, each with its own cars. They all merge onto one giant 8-lane superhighway. They all travel together for a while, and then, when they get close to their destination, they each take their specific exit ramp to go back onto their own little road. That's exactly what multiplexing is. It's the highway system for our data.
Okay, so we can send data and we can share the lines. Awesome, but two huge challenges are still out there. How do we keep our private conversations, well, private? And how do we manage the billions, literally billions of devices all trying to get an address and connect at once? This is where the guardians of the network come in.
We'll spotlight two of these guardians here. First up is IPsec, which stands for IP security. Think of it like an armored car for your data packets. It's a whole suite of tools that scrambles your data so nobody can read it. That's called confidentiality. And it also puts a tamper-proof seal on it so you know it came from the right person and wasn't changed. That's authenticity. Then there's NAT, or Network Address Translation. This is the amazing trick your home router does constantly. See, we ran out of unique internet addresses, or IP addresses, a long time ago. So NAT lets all the devices in your house, your phone, laptop, TV, you name it, share one single public address. It works like a receptionist for your home network, hiding everyone's private identity while directing all the traffic to the right device. And that hiding action also provides a nice, basic firewall.
All right, we've covered the rules, the signals, the sharing, and the security. We've built up our whole theoretical toolkit. Now it's time to put it to the test. The best way to really understand this stuff is to get your hands dirty and apply it. So we're going to tackle a few common problems and use the principles we've just learned to find the answers. Let's get to it.
Okay, here's our first problem. It's about a specific flavor of multiplexing called time division multiplexing, or TDM. Now, the whole idea behind TDM is really simple. Instead of giving everyone a different lane on the highway, you just tell everyone to take turns. It's a repeating cycle where each device gets its own tiny, dedicated slice of time to send its data. So the question is, if you have some number of devices, let's call it n, how many time slots do you need in that cycle?
And the answer is refreshingly straightforward. In TDM, the system is direct, it's fair. Every single device, every single source gets its own unique time slot in the rotation. So, if you need to serve n sources, you need exactly n time slots. It's a perfect one-to-one relationship. 10 devices talking, you need a cycle with 10 time slots. It's as simple as that.
Let's move on to problem number 2. This one takes us back to the nature of signals themselves. When we talk about signals, especially analog ones, you'll hear the term bandwidth all the time. This question gives us a signal that's made up of 5 different frequencies, and it wants to know, what's its total bandwidth? How much space does it take up?
And here is the key thing to remember. Bandwidth is not about adding up all the frequencies. It's much simpler. It's just about the range that they cover. The definition is simply the highest frequency in the signal minus the lowest frequency. So for this problem, we take the top frequency, which is 1500 Hz, and we subtract the bottom one, 300 Hz. And that gives us our answer. The total bandwidth is 1200 Hz. That's the total width of the spectrum this signal needs to use.
Okay, time for a little pop quiz on security. We talked about IPsec earlier, and I called it a suite of tools. Well, this question tests our knowledge of what's actually in that toolkit. It's asking which of the following are key parts of the IPsec framework.
And this slide really shows why IPsec is so powerful. The correct answer is all of them, because each one has a totally unique and critical job. You've got the authentication header, or AH. That's the tamper-proof seal. It guarantees the data is from the right person and hasn't been messed with. Then you've got the encapsulating security payload, or ESP. That's the armored box itself. It encrypts the data so no one can read it. And finally, you've got the Internet Key Exchange, or IKE. That's the secure handshake at the very beginning, where both sides secretly agree on the encryption keys they're going to use. You really need all 3 for a truly secure connection.
And for our final problem, let's circle back to NAT. This is a select all that apply type of question, and it really gets to the heart of what NAT actually does on a practical level, and just as importantly, what it doesn't do.
Okay, let's break down the truths about NAT. First, can it act as a firewall? Yes, absolutely. By hiding your personal devices behind that one address, it naturally blocks unwanted traffic from the internet. So that's true. Second, does it have to recalculate checksums? Yes, it does. A checksum is like a little bit of math attached to a data packet to check for errors. Since NAT literally rewrites the from address on the packet, the original math is now wrong, so it has to redo the calculation.
Third, does it perform IP masquerading? Yes, that's just the fancy technical term for making many devices look like one. But, and this is a big one, it is not a proxy server. A proxy is like a personal shopper that understands your web requests. NAT is more like a mail forwarder that just changes the address on the envelope without ever looking inside. It's a key difference.
So there we have it. We've gone from the pure physics of signals to the logic of networking, from sharing the lines to securing the data, and we even solved a few problems along the way. We've seen how all these fundamental pieces fit together to make our connected world possible. And that kind of leaves us with one final thought. Now that we get the foundations, what do you think is the next great challenge in connecting our world even more? Thank you for watching.